Hello everyone. Today I'm going to discuss with you the P block elements. Okay. So the P block elements, there are six groups. Six groups from group 13 to group 18. So today we are going to discuss the general trends. Okay. The general trends of group 13 to 18. The electronic configuration, atomic radius trend, ionization energy trend, electronegativity trend. These are the trends that we are going to discuss today. Okay. Next, or we will also discuss regarding some of the chemical properties that are the important chemical properties for of the elements present in this group. Okay, so I have this one is group 13 element. So starting with group 13 element, group 13 has 5 elements: boron, aluminium, gallium, indium, thallium. Okay, so these are the elements that you need to remember down the group exactly as same as I have written. Okay, now the electronic configuration for this group is ns2np1. ns2np1, this is the electronic configuration for this group. Now the atomic radius of gallium is less than aluminium. Why is it so? Here the trend for the atomic radius is like this: atomic radius, boron, then gallium atomic radius, then aluminium, then indium, then thallium. As we know that atomic radius increase down the group. Atomic radius increase down the group because of the increase in number of shell. But this one is the exceptional case. Why this is an exceptional case? Why gallium atomic radius is smaller than aluminium? Because before before filling of 4s2 4p1, there are 3d10 electrons, and d electrons have less shielding effect. D electrons are going to shield less the outermost orbit electron. So nucleus will attract this electron towards itself very easily, and that's why the atomic radius now going to decrease. Remember that F electrons have less shielding effect than D, then P, then E. Then S. So this is the shielding effect order. S has the most shielding effect, that it will not allow the nucleus to have its effect on the outermost orbital. Okay, so that's why, because of the poor shielding effect of d electrons, the atomic radius is going to decrease. Now the next trend is this one, we have discussed this one. Now the ionization energy decrease from boron to aluminium is associated with increase in size. Now the ionization energy decreases down the group. But here is an exceptional case that firstly boron has higher ionization energy. Because what is ionization energy? Ionization energy is the removal of electron from the outermost orbital. The energy required to remove an electron from the outermost orbit is orbital of an isolated gaseous atom is called ionization energy. Okay, so now what is the trend for ionization energy of this group? Ionization energy for this group is boron, thallium, then gallium, then aluminium, then indium. This is the trend, general trend for the ionization energy of this group. Now, why this is so? As we move down the group, boron, aluminium, gallium, indium, thallium. Okay. As we move down the group, there is decrease in ionization energy. But this is the exceptional case. Why? Boron has the highest ionization energy. But here, before thallium, before filling of 2s2 2p1, 3s2 3p1, 4 3 4s2 4p1, 5s2 5p1, 6s2 6p1. Okay, before filling of these orbitals, there are 14 f electrons. There are 14 f electrons. If there are 14 f electrons, these 14 f electrons has less shielding effect than d electrons do. Then d electron have more shielding effect. So if they have less shielding effect, they will allow the nucleus to attract these electrons. So that's why it is difficult to remove the electron from the outermost shell. Okay, from the outermost shell it is difficult because they are bound to the nucleus. So the s electrons is not easy, cannot participate in the cannot participate in the bonding easily. That's why thallium, after that gallium, because of the three d10 electrons, because of this d10 electrons, the outermost electrons will not be, the nucleus is going to attract this outermost electron, and it is not easy to remove this electron from the outermost orbital. After that, aluminium and the indium is the last one. Okay, now the next trend is electron. Firstly, successive ionization energy. Remember, successive ionization energy means delta H1 for a particular element, then the delta H2, then the delta H3. Delta H3 is greater than delta H2, which is greater than delta H1. Why it is greater than delta H3 is greater than delta H2 than delta H1? Because as we are forming more and more cationic species, then then there is more effect of nucleus on the less electrons. That's why this is going to increase. For example, suppose I am having boron plus, this doesn't exist at all, boron plus 2, boron plus 3. Okay, boron plus 3 is more than boron plus 2 is less than which is more than boron plus 1. Okay, now here this one is for the ionization energy, then the electronegativity down the group decreases from boron to aluminium and then increases marginally. This is the electronegativity trend. Now the physical properties of these groups, they are non-metallic in nature, hard and black solids exist in many allotropic forms. Boron has high melting point while the other have a low melting point. Density increases down the group as the molecular mass is going to increase, the density of these elements is going to increase. Now there are some of the chemical properties and you need to remember this. How the chemical properties relates with the oxidation state, because oxidation state will tell us how many bond is going to be formed or how many ionic bond or covalent bond is going to be formed by these elements. Now, the oxidation state of the element +1 and +3. Okay, +1 and +3. Why it is +1 and +3? Because, see, if I'm going to tell you what should be the oxidation state. Oxidation state is the number of electrons that can easily participate in the bonding. Okay, boron is going to form in the +3, although it is not going to form the +3 cation because it wants to be in covalent bond. But here it can show +3, but the thallium is going to show +1. Its most stable oxidation state is +1. Why it is +1? Because before in thallium, before filling of s and p orbitals, there are 14 f electrons also. 14 f electrons are where can rarely shield the outermost electrons from the nucleus. That's why this nucleus has a great effect on the s electrons of the outermost orbit. Nucleus attract the s electron, and it is not easy to remove this electron from the outermost orbit, and only that's why the p orbital electron is going to participate. That's why only +1 oxidation state uh, um, is stable for the thallium. Now, what is this? This is due to inert pair effect. Inert pair effect. What is inert pair effect? Inert pair effect means the reluctance of participation of s electrons, the reluctance of participation of s electrons in bonding is called inert pair effect. Okay, due to poor shielding effect of p and f electrons. So this is the according to oxidation state. Now you can see if an element is going to react with O2 means oxygen. If an element is going to react with N2, how we can form E oxygen. Okay, so elemental oxide. Okay, element has its oxidation state 3. E2O3 will be the formula. E2O3. Now element with nitrogen. So then element has 3 oxidation state, nitrogen has 3 oxidation state. So you will have E3N3, but the overall formula is En. Okay. This is in heat. In the presence of HCl, aluminium 3 plus and chlorine and hydrogen is going to form. In the presence of halogen, how it will relate? X2. E element has 3, oxidation state of X is 1, EX3. EX3. So these are the formulas that is related to the 13th group. Okay. Now, there are trends and anomalous properties of boron. What are the trends and the anomalous property? Boron, except in boron, all the elements form MOH4 minus and MH2O6 2 plus exist in the aqueous media. Boron trifluoride react with the Lewis base. How it will react with the Lewis base? This is an important question. Maximum covalency of boron is 4. Why the maximum covalency of boron is 4? Because this is boron is a second period element. Boron is a second period element. So it can form only 4 bonds. Only 4 bonds. Because it doesn't have vacant d orbital. Now, this is boron according to boron. Now, why boron trifluoride act as a Lewis acid? Boron trifluoride will act as a Lewis acid because around boron only 6 electrons are there. Electrons are there. That's why it will act as Lewis acid. So, if it is a Lewis acid, it will react with the Lewis base. Now, there is some trend that I want to discuss, that if I ask you that boron trifluoride, boron trichloride, boron tribromide, boron triiodide. If I'll ask you which one is more acidic, which one is less acidic, this one will be the most acidic one. Why? Because here the case of back bonding occurs. Here the case of back bonding occurs. Why the back bonding? Because boron has p orbital. Boron has p orbital in it, and p orbital, which type of p orbital? 2p orbital. Here it is also 2p orbital. So it is going to back donate the electrons. Back donate the electrons from itself to the boron p orbital. So it is decreasing the Lewis acidity. It is decreasing the Lewis acidity of boron. Here, in the case of this one, boron trichloride. Boron trichloride. Now, chlorine cannot back donate easily to the boron p orbital. Okay, this is 3p orbital, this one is 2p orbital. Because 2p 2p overlap is more favorable than 2p 3p overlap. That's why it is not decreasing the Lewis acidic strength of boron as that of the fluorine. Okay, so that's why it is increasing from here to here. Now the next question is importance of the boron compound. So here are some of the important formulas and the compounds related to it. This is borax. The formula of borax that you need to remember: Na2B4O7.10H2O. It's a white crystalline solid. Now the next one, if borax is going to attacked by the water molecule, then you are going to form 2NaOH plus 4H3BO3. Now the Na2B4O7.10H2O on heating, it will give Na2B4O7 on heating 2NaBO2 plus B2O3. This is borax bead test is used for the identification of this boron. Next one is orthoboric acid. It's a white crystalline solid and a soapy touch. Just need to know that this is orthoboric acid, BOH3, Na2B4O7 plus 2HCl plus 5H2O. Give 2NaCl plus 4BOH3. Now BOH3 on reaction with H2O, it will give BOH4 negative. H3BO3 on heating give HBO2 on heating B2O3. Just need to remember the reactions. Okay. Now the diborane. Diborane, how you can form the diborane? On reaction of BF3 with lithium aluminium hydride, you will get B2H6 plus 2LiF plus 3AlF3. 2NaBH4 on reaction with iodine, it will give B2H6 plus 2NaI plus H2. 2BF3 on reaction with NaH on sodium hydride reaction, it will give B2H6 and 6NaF. Now this is a colorless toxic, boiling point 180 Kelvin, it catches fire. Now the next one is B2H6 on reaction with oxygen, it will give B2O3 and 3H2O. B2H6 on reaction with water, it will give BOH3, means the orthoboric acid, and 6H2O. These one are the important reactions. What are they? We have B2H6. B2H6. It's a diborane kind of structure. You need to remember the structure for this. These are the bridging hydrogens. These are the terminal hydrogens. Bridging hydrogens that connect both the boron. Okay, so these are the terminal hydrogen. These are perpendicular to plane. Perpendicular to plane. All of these atoms, like two boron and 4 hydrogen, are in the plane. This will act as Lewis acid because it's a boron. Boron has only 3 bonds, but the 4th bond, this whole B2H is a 3-center 2 electron. Okay, 3-center 2 electron. Now the Lewis acid is going to be attacked by the Lewis base. Okay, so Lewis base here is B2H6 B2H6 is a Lewis acid and Lewis base is NME3. It is going to form the adduct. So you will get 2BH3 and Me3. It's an adduct. Now B2H6 on reaction with CO. CO also has a lone pair. So you will get here 2BH3, 2BH3, CO. So this is the adduct that is going to form. Okay. Now, in front of NME3, you need to put 2. In front of CO, you need to put 2. Okay. Next one is, if V2H6 is going to react with ammonia, it will give us borazine B3N3H6. Firstly, it forms this complex compound where it is unsymmetrical breaking of the B2H6. Unsymmetrical breaking, how it is going to form, I'm going to show you in a different structure. Okay, so the unsymmetrical bonding will be like this. Okay, symmetrical bonding when both the boron has hydrogen, 3 hydrogen. Here it's an unsymmetrical bonding. So you are going to get BH2 NH3 2 positive, BH4 negative, and on heating it will give borazine. Borazine is B3N3, borazine B3N3H6. It's an inorganic benzene. Inorganic benzene. Now the uses of boron and aluminium and their compounds. Okay, boron fibers are used in making bulletproof vests and light material for aircraft. Borax is used in manufacturing heat resistant glasses. Aluminium is used in packing, utensil making, construction and transportation industry. So these are the importance that is for the boron and the aluminium and their compounds. Now the next group is, this is for the 13th group. 13th group. Now the next group is group 14 element, and there are the trends. Electronic configuration. Like boron, like 13th group, we have the electronic configuration for group 14th, that is NS2NP2. Now the covalent radius for this group, it increases from carbon to silicon, and from silicon to lead a small increase is observed. Why there is a small increase in silicon to lead? Silicon to lead, there is a small increase in atomic radius, because from germanium, before filling of 4s2 4p2, there are 3d10 electrons which have poor shielding effect. Because of this poor shielding effect, the outermost orbital is more likely to attract with the nucleus. That's why the increase in atomic radius is not that much. Okay, so here we have an increase is observed. Decrease down the group, ionization energy decreases down the group because the nucleus effect on the outermost orbital is going to be less at this time. Okay, nucleus effect on the outermost orbital is going to be less. Now the next one is electronegativity. Electronegativity of group 14 is more than that of group 13. Why it is more than that of group 13? Because of the increase in the positive charge on the nucleus. That's why it is going to attract the electrons more effectively. It is going to attract the electrons more effectively than the 13 group elements. Now the physical properties of the group 14 element, they are solid in nature. Carbon and silicons are the known metals, germaniums are metalloids, silicon and tin are soft metal. Melting point and boiling point of this group elements is higher than that of group 13 elements. Why? Because of the increase in binding. If the increase in binding or increase in molecular mass, then there are increase in van der Waals forces. That's why it will increase the boiling point of these elements. Now, what are the chemical properties? Chemical properties exactly depends upon the oxidation state. Now, again, the trend related to the oxidation state, how it is possible. Carbon, silicon, germanium, tin, lead. Okay. So the two oxidation state that can be possible. Now always remember, if there is a decrease in oxidation state, then it will decrease by 2, because all the s electron is going to get removed. Okay. Sorry, all the p electrons is going to get removed. Here the electronic configuration is ns2 np2. P electrons are the outermost, but the s electrons are held strongly by the nucleus. Held strongly by the nucleus. Why? Because of the presence of 14 f electron before the lead. Lead, if you want to discuss that what is the stable oxidation state of lead, then it is +2 oxidation state. And if you have the formula Pb O2. Here the oxidation state of lead is +4. It will convert into +2. Try to convert the lead oxidation state into +2. You will get the answer of your question, because they are going to ask you the MCQ type of question. So why the 14 f electron? The poor shade, because of the poor shielding effect of 14 f electrons. The poor shielding effect of 14 f electrons, the s electrons cannot take part in the bonding. Cannot take part in the bonding. Okay. Now the next one is, it can form oxides on heating. Carbon, silicon, germanium, and lead are not affected by water, but the tin affects by the water. Tin 2H2 on heating, SnO2 plus 2H2. It can form halides of the formula MX2 and MX4. Halides, M can have +4 value, X can have -1, M can have +2 value, X can have -1, M, X4, M, X2. Okay. So the next one is important trends and the anomalous behavior of carbon. So this is very much important, that you need to remember that each and every element, each and every first element of the every group has some anomalous behavior, some different behavior than the rest of the elements. Okay. It has high ionization energy, because of the small size, and its orbital is very near to the nucleus. High electronegativity, and unavailability of a d orbital. High ionization enthalpy, because of the smaller size, high electronegativity, and the unavailability of d orbital. There is no d orbital available for bonding. Now the next one is, it shows carbon form p pi multiple bonds. So p pi multiple bonds are like this. In alkene there are p pi multiple bonds. So we have the p pi multiple bonds. Next one is, it can show catenation. It has carbon can show catenation property. Catenation property which has the self-linking tendency. Linking tendency. Okay. Now the allotropes of carbon. There are 3 allotropes that I have mentioned here: diamond, carbon, and full ring. These are the allotropes of carbon. Here we have the uses of carbon. Graphite composition are used in tennis rackets, fishing rods, aircrafts. Graphite is used for electrodes in batteries and industrial electrolysis. Carbon black is used for black ink and as a filler in automobile boxes. Diamond is used in jewelry. So these are the uses of carbon. Now the important compounds of carbon and silicon. So here we have the important compounds, that is carbon monoxide, which is formed from carbon and oxygen reaction in the limited supply of air. If the limited supply of air is there, then only the formation of carbon monoxide. If the supply of oxygen is more, that means it is in excess, then the formation of carbon dioxide is formed. Is there, but in the presence of limited supply of air, you are getting a toxic compound, that's 2CO. Then HCOH on heating in the presence of concentrated H2SO4, you are going to get H2 and the CO. Carbon dioxide, carbon dioxide is going to form carbon with oxygen on heating. Okay, in the presence of air, CO2 is going to form. If a methane or the hydrocarbon is going to react with oxygen, you are going to get the CO2 and the 2H2. Here the silicones group of organosilicon polymer with R2SiO repeating unit. This you need to remember. Silicates, the structural unit of silicate is SiO4 4 negative. Silicon dioxide is covalently bonded to 4 oxygen atom, and the zeolites, which is used as catalyst in the petrochemical industry. Water gas, this is synthesis gas and a mixture of CO and H2. And the electronic configuration for this group, for the electronic configuration for these groups for the p block element is ns2np126, means for the boron family ns2np1, for carbon family ns2np2, for nitrogen family ns2np3, for oxygen family ns2np4, for halogen family ns2np5, for your noble gases ns2np6, except helium. Okay, then the producer gas formula is CO and N. These are the formulas that you need to remember. Okay. Now the next one is this one. P block elements. So the group 14, almost the same trend. Atomic radius and ionization enthalpy, some of the melting point and boiling point I am going to discuss. 15 group elements. Group number 15 has these elements: nitrogen, phosphorus, arsenic, antimony, bismuth. Again, the anomalous behavior of nitrogen, it has the highest ionization energy, high electronegativity because of the small size. D orbital not available. So these are some of the anomalous property of each and every element in a group. Now here the phosphorus has tendency to form the allotropes. There are 3 allotropes: red, white, and black. Red phosphorus, white phosphorus, and black phosphorus. White phosphorus is the most reactive phosphorus. Most reactive phosphorus. So these are the important points that you need to remember. Nitrogen has high boiling point because of the hydrogen. NH3 has high boiling point because of the hydrogen bonding in the molecules. Okay. Now, what I'm going to discuss with you, the group 16 elements. Group 16 element has the electronic configuration ns2np4. Atomic and ionic radii increases down the group because of the increase in the shell number. And shell means number of shell number is going to increase, the principal quantum is going to increase. That's why the atomic and the ionic radii is going to increase. Now the ionization energy. Ionization energy is going to decrease down the group because the nucleus effect on the outermost orbital is going to be less after some time. Okay, with increase in shell, the nucleus effect on the outermost orbital electron is going to decrease. That's why the electron can be easily uh, removed from the outermost orbital. Now the next one is electron gain enthalpy. Electron gain enthalpy, oxygen has less negative electron gain enthalpy than the S. Actually, if there is any formation of, or there is any increase in electron in the orbital, then there is a release in the energy that is in negative. Oxygen cannot gain the electron very easily because of its small size orbital, that is 2p. 2p cannot have the more electrons because of small size. The electron is going to repel each other. That's why they are not going to attract the electron. Oxygen is not going to attract the electron. So oxygen electron has less electron gain enthalpy. Now the trend for the electron gain enthalpy in this group is very important. This is electron gain enthalpy trend. Electron affinity trend. Electron affinity is very much high for sulfur, then selenium, then tellurium. Oxygen has the least electron affinity. Okay, this you need to remember. Now the next one is electronegativity. It decreases with increase in atomic number. Electronegativity also depends upon the nucleus effect on the outermost side, because electronegativity is the tendency to attract the shear pair of electron towards a more electronegative atom. And if atom is more electronegative, that depends upon the nucleus charge. If nucleus charge is more on the outer side, then it will attract the electron more easily. Okay, so this is electronegativity. After that, the physical property, oxygen and sulfur are non-metal, selenium and tellurium are metalloids, and lead polonium is a metal. All exhibit allotropy. Allotropy is there. Melting point and boiling point. Melting point and boiling point increases down the group. Why it increases down the group? Because of the increase in molecular mass, there is an increase in vulnerable forces of attraction. If the vulnerable forces, if any type of interaction is going to increase, then it is difficult to break the interactions from that, and that's why you need to provide a lot more temperature than initially if there is no interaction between the molecules. Okay, so that's why melting and boiling point increases down the group. Now the chemical properties depends upon the oxidation state. There are variable oxidation state. We can't say that the oxidation state is +6 or +4 only, but there are +2, +6, +4. There are many important oxidation state. Now the reactivity with halogen. See, F negative is more reactive than Cl negative, which is more reactive than Br negative, which is more reactive than I negative. Why F negative is more reactive? Because F, because of its smaller size, electrons are there, it will react with the another element easily. Okay, now the oxo acids of sulfur. What are the oxo acids of sulfur? There are three oxo acids that have mentioned here. I'm going to tell you another one too. H2SO3. Remember that the oxidation state of sulfur, you need to calculate the oxidation state. How you can calculate H2SO3? So you have 2 plus X for the sulfur minus 6 is equal to 0. X is equal to +4, the sulfur oxidation state. This is H2SO4 plus 6. You will calculate the plus. This is Marshall acid. They can ask you which acid has peroxy linkage. Here the peroxy linkage is present. Peroxy linkage. And it's an important linkage. One more important compound of sulfur that has peroxy linkage is H2SO5. 5 oxygen and 2 hydrogen. This is the peroxy linkage. Now the next one is the preparation of dioxygen. Preparation of dioxygen from KClO3. This is an important compound, KClO3. On heating in the presence of manganese dioxide, it will give you KCl and oxygen formation. The properties of these elements, properties: calcium on reaction with oxygen, it will give the formation of calcium oxide, that is quick lime or calcium oxide. Then the aluminium on oxygen reacts to form, means the basically the oxides is going to form on reaction with oxygen. Now this is the reaction in the contact process to form the sulfur trioxide, SO2 on reaction with O2 in the presence of the vanadium pentaoxide, you will get sulfur dioxide. HCl on reaction with O2 in the presence of CuCl2, it will give the Cl2 and the 2H2. Now the next group is group number 17. Group number 17 is also a very important group. Here the occurrence, fluorine and chlorine are fairly abundant, while bromine and iodine are less one. Chlorine is very much important because they have chlorine has many importance in the biological activities also, and it is there in the synthesis of chloroquine. Okay, quinine is used as a medicine for the malaria treatment, chloroquine is also used somewhere. Now the journal electronic configuration of group 17 element is ns2np5. The atomic radius smallest in the period but increases from fluorine to iodine. Why it is smallest in the period? Boron, then carbon, nitrogen, oxygen, fluorine. Fluorine, because of the increase in charge here, +7 charge in the nucleus, sorry, +9 in the nucleus, so they can attract the electrons more easily because the electrons are arranging themselves in that shell only, and the nucleus has most effect on this shell. Okay, that's why, because of the increase in the positive charge, that it will attract the outermost electron towards itself easily. It decreases the uh, shell, it decreases the size of the shell. That's why the fluorine is having less size than the other elements in the period. So atomic radius, and after that the ionization energy is going to decrease down the group again, because of the increase in the shell number down the group. The nucleus effect is going to be less on the outermost shell electrons, and it is easy to remove the electrons from the outermost shell. Next one is electron gain enthalpy. Group 17 has less negative down the group electron gain enthalpy. Now the electron affinity trend. Electron affinity. Electron affinity means tendency to gain an electron, the energy released when there is a gain of electron by an isolated gaseous atom. Now fluorine has less electron affinity than chlorine, after that bromine, then iodine. Although fluorine is more electronegative, but they, if it will attract the electron, then there are repulsions, 2p repulsions, 2p electron repulsion. Okay, so if there is increase in repulsion, then when it is not easy to remove, then it is not stable. That's why chlorine has the orbital 3p, in which if we are having electron, then the repulsion is somewhat less than that of the fluorine case. That's why this is the electron affinity trend. Electron affinity trend. Okay, for the group 17 elements. Group 17 element. Now, after that, mm, physical property. Fluorine and chlorine are gas, bromine is liquid, and iodine is solid. Um, fluor, uh, fluor, uh, Fluorine has no color, it's a colorless gas. Chlorine is yellowish brown, yellowish green gas. Bromine is a liquid, reddish brown liquid. Iodine is a solid, violet crystals like solid. Now the melting point and boiling point, it increases with the increase in atomic number. The increase in melting point all depends upon the increase in vulnerable radius, vulnerable interaction, and vulnerable interaction is going to increase with the increase in molecular mass. Okay, if the molecular mass is going to increase, then the interaction is going to increase due to vulnerable forces. That's why melting and boiling point increases down the group. After that, chemical properties. Chemical properties, here are some of the chemical properties of a group 17 elements. All the elements of halogen element exhibit -1 oxidation state, while chlorine, bromine, iodine can exhibit variable oxidation state, that +3, +5, +1 and +7. Here is the difference of two electron. Remember always that two electrons, on unpairing the two electrons, the these type of oxidation state, these four oxidation state is going to be exhibited by the these elements. Now the reactivity towards hydrogen. HF is more reactive than HCl, it is more reactive than HBr, it is more reactive than HI. So this is the reactivity towards hydrogen. Reactivity towards oxygen, fluorine form OF2 stable and O2F2. These are the compounds that is formed. Reactivity towards metal, NF is more reactive than NCl, than NBr, because it is easy to break the bond, because fluorine is more electronegative and it is going to form F negative, and M can easily donate the electrons. Next one is the activity towards other halogen. These are pseudo halogens. So more electronegative element is on the terminal, and the less electronegative in and thus at the center. Okay, like scale F3, BRF5. This is the formula that is for the halogens. Okay, this is interhalogen compound, no, the pseudo halogens. Pseudo halogens are the different compounds. Okay, now the next one is from chlorine. How we can prepare chlorine? Chlorine we can prepare from MnO2 plus 4HCl, giving MnCl2 plus chlorine plus 2H2O. The Deccan's process. Deccan's process, 4HCl plus O2 in CuCl2 gives 2Cl2 and 2H2O. Now the properties of chlorine. It's a greenish yellow gas with pungent and suffocating odor, heavier than air. Aluminium on reaction with chlorine gives 2AlCl3. Hydrogen on reaction with chlorine, it will give 2HCl. H2S on reaction with chlorine, it will form the sulfur salt. 2HCl to 8NH3 on reaction with 3HCl2, it will form NH4Cl and N2. NaOH, it's an important reaction. NaOH on reaction with chlorine, in the presence of cold and dilute solution, you will get NaCl, NaOCl plus H2O. If NaOH, hot, and chlorine, you will get NaCl plus NaClO3, chlorate structures. Okay, this you need to remember. Now the next one is 2CaOH2 on reaction with 2 chlorine, you will get bleaching powder CaOCl2 plus CaCl2 plus 2H2O. Now the next one is CH4 and chlorine in the UV light, CH3Cl plus HCl. Now C2H4 on reaction with chlorine, RT room temperature, C2H4 Cl2. FeSO4 on reaction with H2SO4 and chlorine, Fe2SO4 3 plus 2 HCl. SO2 plus 2H2O in the chlorine reaction with these chlorine SO2 2H2O, it will give you H2SO4 and 2HCl. Cl2 on reaction with water, you will get 2HCl and oxygen. Interhalogen compounds. There are interhalogen compound X dash sp3 linear structure. It's sp. It will be sp. If there X dash X3 dash sp3d T shape, that depends. X5 sp3d2 XX3 sorry XX7 sp3d3. This is a pentagonal bipyramidal. Now the next one is group number 18 elements. Group number 18 elements, all except radon occur in atmosphere. Radon is a radioactive element. The journal electronic configuration NS2 NP6 except the helium. Ionization energy of this group is very high. Why? The group element has high ionization energy because of the filled p orbital. Filled, half filled and fully filled p orbitals have extra stability because of the symmetry present there, because of the stability present there. Now the atomic radius. Atomic radius increases down the group. Electron gain enthalpy. It's a largely positive. It will be largely positive because electron gain enthalpy largely positive. Why? It doesn't want to attract any electron. If it doesn't want, if anything that occurs opposite to the behavior of the element, then it is not good. Then a physical property, the monoatomic element colorless, odorless, tasteless, and sparingly soluble in water. Melting point and boiling point is low because of the interactions are low in the case. Then the chemical property. These are the least reactive xenon fluoride compounds are formed XCF to XCF4, XCF6. Xenon oxygen compound XCO3, XCOF2, XCOF4. So these can be related to each other, but I am going to show you some of the structures because it is important to know it. So how we can calculate the hybridization? For calculating the hybridization, first you need to choose the central atom plus number of monovalent atom plus charge of anion minus charge of cation, divide by 2. This you need to calculate for the hybridization. Now Z value, this I am calculating Z value, the steric number value. If the steric number value is 2, then the hybridization is SP, and the hybridization is right SP, and the structure or shape or geometry is linear with the steric number. Trigonal planar, it is 4 sp3 tetrahedral, it is 5 sp3d trigonal bipyramidal, octahedral, 7 sp3d3 pentagonal bipyramidal. This is the important bipyramidal. Now if I'll tell you XCF2, the number of valence electron of the central atom. Valence electron is 8, number of monovalent atom is 2. So 10 by 2, it's 5. 5 sp3d structure. Now only 2 are bond pair and 3 will be the lone pair. So you are going to put the lone pair on the electronegative side like this. Shape is linear. Here you can see there is not mentioned the structure geometry of the XCF2. Then XCF4, I want you to calculate with me. XCF4 is 8 plus 4 divided by 2, 12 divided by 2, that is 6. 4 bond pair, 2 lone pair. Then firstly 6 is for octahedral geometry, sp3d2, XC, F, 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 lone pair on this side, lone pair on this side. So shape of this is square planar. There is a difference in shape and geometry. Geometry contains both the lone pair and the bond pair, but the shape is only of the bond pair. Okay. Then it's XCF6. XC 8 electrons, F has 6 electrons. 14 by 2, 7. sp3d3, pentagonal, bipyramidal. Sorry, it's a distorted octahedral structure. Very important. sp3d3, distorted octahedral kind of structure. sp3d3 because of this 7 electron. Here the lone pair is present in this condition. Okay, so this is important for XCF6. Now I'm going to calculate for the oxygen. Xenon oxyfluorides, HCO3. Now this is a divalent atom and I'm not going to consider in the hybridization. XC, so you need to calculate the Z. 8 divided by 2, there is no positive and negative charge. So 4. Here at least 3 sigma bonds are there with the oxygen and 1 lone pair. So XC, the lone pair, like this pyramidal type of structure. Shape. Geometry is tetrahedral. Geometry is tetrahedral. Now the next one is XCOF2. XCOF2. So this is a central atom. This one monovalent atom. This one is a divalent atom. To calculate Z, central atom has 8 electrons, monovalent 2. Now, firstly 3 sigma bonds, 3 bond, 2 lone pair. Hybridization is sp3d, trigonal, bipyramidal. Now XC, this will be the shape because lone pair on this side F on the axial position and oxygen on the. This is a T-shaped structure. Although the geometry is triangle bipyramidal, but it's a T-shaped structure. Now the next one is that is remaining HCOF4. Again, the central atom, the monovalent atom, and the divalent atom. Central atom, monovalent atom, divalent atom. Z, to calculate Z, X is 8 plus 4 divided by 2. 12 divided by 2, it's 6 d2. Okay. Octahedron. 5 lone pair, 1 lone pair. XCO F4. It's a square pyramidal type structure. So these are all the structures that is mentioned in NCRT also. So you can check from there also. So this is the summary for whole of the P block chapter. I hope you are clear with your concept at this time. Thank you so much for watching.